thought, well, so I started looking into the science, and I did the sums. Is there enough ice in Greenland? Can anybody tell me, have you done this same thing? The area of Greenland by 3 kilometers, that's how the average depth of ice in Greenland. That's a lot of ice. And you do the sums, and yes, it really would be enough to put the sea level up 7 meters. There's a whole pile more behind the science there. And luckily Greenland isn't melting too quickly, so we're still safe where we are. But it got me interested in the science of climate change and what we're doing. And so I've started, I've been all sorts of things along the way. I've been a protester, I've run for parliament, I've done silly things like sailing to Newcastle, to the biggest coal port in the world. But I've also been in Citizens Climate Lobby for several years, and I think that's the best bet. That's talking to the politicians in their office. Haven't achieved enough yet, but it's useful. You need to. Is that better for those? Yes. Right. Good. Thank you. Okay. So anyway, so I've started sharing this story with people, and this is one of the 5 stories I find the carbon story, and it's a bit of a chemistry lesson. Who remembers their chemistry and physics from back high school days? Oh dear. Okay. Well, I'm going to do in 5 minutes what your teacher took, 2 years or 3 years trying. But it's a fairly narrow view of it, but you'll get the idea. Now I've got a controller here somewhere. Gotta get the right button. So my first experience, carbon, was what your experience a bit like mine. I lived in England when I was a kid, when I was this age. And I remember playing with the lounge chairs, having the cushions from all around the lounge room, all stacked up neatly on the sofa. And I would take them off there, and I would go and unload them into empty the sacks of coal into the coal cellar, like the man on the truck. That was my truck with coal on it, because we used to get coal delivered. Now, I didn't actually clean chimneys like this guy, but my thought of carbon was that sooty stuff around the chimney, around the fireplace. So that's what I thought carbon was. But carbon comes in all sorts of different ways. There's coal, of course, we all know carbon. And coal is quite a pure form of carbon. It's something in the order of 80–90% carbon. And it can actually melt if you heat it up enough under the ground, and then it resolidifies. It can be what looks like a glacier form. But this stuff we have in our pencils, this graphite, it's a slightly different form, sort of black. It's another form of carbon. But this is the real surprise. It's diamonds. They're pure carbon. And it looks so different. It's got a completely different type. Graphite is one of the softest things in the world. Diamond's one of the hardest. It is the hardest. And then you've got other things like carbon fiber, which is a more recent. So what is this stuff carbon? We have also the knowledge that, it burns. It burns so readily. It's got a lot of energy in it. And this is coke being made by heating up coal and driving off the different forms of carbon and some impurities, and leaving behind a more pure form, which is used in the coke ovens. Well, it's used in steel making. This is from the coke ovens. But so this is where we get into the chemistry. What is carbon? Is everybody familiar with the periodic table? Yeah. This blew my mind when I learned this fact. The universe, when it first was created, only had hydrogen in it. That was all that was produced in the original universe. And all these other elements, which are multiples of the hydrogen, where you have one proton, one neutron, electron, the very simplest form of atom, right up to the more complex things. All of these elements are generated in the middle of stars because who knows what the hydrogen bomb does? It takes two hydrogen, forces them together, and there's energy given off when you do that. You need an awful lot of pressure and energy to get it to react. And two hydrogens then become one heat, number two. And so on and so forth. And this process happens in the middle of stars. And yet our Earth is made up of a whole pile of those elements, not every one, so we've got examples of all those elements. So where did they come from the universe? They came from supernovas, from stars going through their whole lifetime, and at the end of their life, they have a supernova, and they explode, and all of these different things that have been produced inside them are spread around the universe, and then they recombine to make other things, planets and more suns and so forth. So we are stardust. What makes us up? What makes this whole world up? Stuff that was in a supernova in the past. This blows my mind. We've been in the middle of a sun. So anyway, I'll get back to the point. So, carbon over here. I've got to remember the people. Hi there. I've got to stay in front of you. Sorry. Carbon is number 6 on this list. It's near nitrogen and oxygen. It's in that safe zone. And when you put two elements together, hydrogens together and heliums together, and you force them together, you get energy out more than what you put in to do that. But as you get beyond those early elements, the nitrogen, oxygen, so on, when you break them down, you get more energy out than the energy you put in. So we've got hydrogen bonds which create energy, but we've also got plutonium bonds which create a lot of energy too. And that's by splitting the atoms together. So these things go on. I don't into physics too much here. Get back to carbon, Tom. So we've got carbon is number 6 element, and it's a special one. It's the 4th most common element in the universe. Mostly, as you come down the periodic table, they get fewer, less and less. But the special thing about carbon is it's number 6 on the table. It's got 6 of everything, and it's got 4 electrons in the outer shell, if you remember your chemistry. And that means it's got 4 bonding things. It's got like 4 arms out there. It wants to join with other things. So because of that, it's unique in that not many elements have so many options for bonding. So it likes bonding. It likes bonding with itself. So it will join up with other carbon atoms and have little bonds, and it'll get some of these fancy shapes. Diamonds are a form of bonding, but it's in a lattice, and it's a continuous lattice, like a crystal. B there is graphite, because carbon makes little thin sheets. So it's like little sheets of paper that you have in graphite. That's what makes it like a lubricant. They slide over each other so well. And then there are so many different other forms, and including these tube type things, which is what they tend to use, which is like a continuous chain of carbon. That's what they use in carbon fiber in order to get strength, because it's like one continuous compound. And of course, it loves bonding with other things. Hydrogen is very common, loves bonding with hydrogen. So you would have heard of hydrocarbons. It's been a lot in the news. The hydrocarbons are like a form of carbon that where with hydrogen, it takes many different forms, the little patterns. It starts with methane up there. It's the very simplest. It's natural gas, or what we have as gas that we burn. It's a light element, and therefore it's a gaseous form in a normal state. And then there's ethane and propane, butane, and different more complex forms, which are all gases. And then you've got the liquids, which come in all levels of thickness. And so the main components of petrol in the middle there, and you'll recognise perhaps some of these things. Anybody working in the steel industry, BTX is what comes out of what they get out of the coal companies, and they use that for making different chemicals. Anyway, they can separate these different hydrocarbons that we get in oil and gas and coal. We can separate those into all the different classes by putting them in like a torch. You heat them up and a gas is given off and you collect the gas like you do in distillation. And there are so many different levels of that. So a distillery of a refinery of oil basically heats up the tarry oil that they get out of the ground, it gets the lighter stuff out, and through different levels, and they pull off all the different petroleums and gases that you can produce. So this is what happens when we separate those things. We end up with all this. As you can see, there's a lot of hydrocarbons, spending too much time on that. Carbon also likes to join with water, and we would all be familiar with the term hydrocarbon, or sorry, carbohydrates. Carbohydrates are where you have carbon and hydrates, water-based things. And you would recognize glucose, fructose, and sucrose, lactose, maltose. You've heard of these things. They're the sugars that we have. These are foods. These are things that sustain us. So, but also, a lot of our drugs are based on carbohydrates. Aspirin, ibuprofen, I can't pronounce that one, amphetamine, and so on, adrenaline. These are things that are naturally occurring and some non-naturally, different forms of things that affect our bodies. And carbon simply loves oxygen. Now, oxygen is, most things will burn in oxygen, they'll oxidize, and carbon is no stranger here. And so the lowest common denominator for carbon is when it's burned in oxygen, because when you burn any of those hydrocarbons or any of the carbohydrates in enough oxygen, it will burn and the oxygen will grab the carbon and grab it away from anything else that's there. And the reason that is because the lowest energy level that carbon can have in our environment is when it's joined with oxygen. So it's like you've taken all the energy out of it and left it at its lowest state. In order to get it back up to a high energy state, you've got to take that the oxygen away from it again. And you would probably all be familiar with the term carbon monoxide, which is a poisonous gas, as opposed to carbon dioxide, which is not poisonous. And the reason for that is that when it gets into our bloodstream, the carbon monoxide takes up the space in your red blood cells that oxygen wants to get into in order to get oxygen around your body. And it will slowly suffocate your body by taking away the option for getting the oxygen around it. So that's why you don't spend too much time in a room with a car running with its engine. It's because cars produce a certain amount of carbon monoxide when they're burning fuel. And you don't want to be breathing that carbon monoxide in because it builds up in your body. So you can burn carbon monoxide to make carbon dioxide bigger. You have to heat it again. So it's just a matter of that's what comes if you don't have enough oxygen around it. So, right. Now, even diamond will burn. It's because there's more energy in burning. It's more energy to be had in a diamond than in the carbon dioxide you produce by burning it. So the energy will come out. You have to heat it up really hot to do so. So all forms of carbon will want to get down to that lowest level if you heat them or create a flame to start them off. Now, carbon also likes to party. Polymerizing with different friends. Carbon likes to get in a chain format. And you will have heard of all of these different uh, polyethylene, polypropylene, polybutylene, polyurethane, polyester, polycarbonate, vinyl polymers, PVA, PVC, PVA, polystyrene are just a few of all of those plastics. Carbon is behind plastics, and in fact, you can get foodstuffs which become plastic. If you know the pizza with your cheese, heat it up, does certain things to it, it starts to form chains and becomes quite strong. So carbon's involved in all these things. And the most common one is polyester, which is what we use in pet bottles. And then there's proteins. Carbon is the basis for proteins. Hey, that's another part of our food. There's a thought there. Proteins. Does anybody recognize what protein, what particular structure we're looking at here? The spiral and the side? DNA, yes. And this is what makes DNA. It's proteins. And you can see the complexity of how many different things are involved. And yet all our DNA is made from those, there's actually 4 basic proteins there, that T, A, C, and G are 4 different proteins that join together in this chain to create DNA. And the wonder of life is that those, the rungs of the poles of the ladder, which are twisted around, will separate within our cells. They separate, and then they find another, all loose, like there's a soup of proteins in the cell with them, and they'll join up and form the other half of the chain. And so that these things are able to reproduce. That's what life is all about. Reproducing this DNA is what life is all about. It's what life is. So we are 18% carbon. That's how much carbon is inside us. We know that we're 80% water or thereabouts, but that's because we've got oxygen and hydrogen combined together to make water. But that water is used up in the DNA as well, and most other things. It's involved in the process. But you can see there's a large portion of carbon, and yet carbon on Earth is only a small portion of the total. It's only 0.073% of the planet. So we are lucky we've combined a lot of that carbon together to make life on the planet. Now, there's carbon on most planets, but we are the only planet we know of that has life, so we're pretty unique in that regard. We find no evidence of it elsewhere. Food. Did you know that food would not be food if it does not contain carbon? Not surprising after what we've just learned, probably. But think about it. It would not be food if it didn't have carbon in it. And the reason for that is basically we need that carbon to burn up in our bodies to grow our bodies, but also for energy in our bodies. We produce carbon dioxide by eating food, and our body burns it, uses the energy, and creates, it creates carbon dioxide in the process. So we're breathing out carbon dioxide as we breathe oxygen. It wouldn't be food without carbon. And it's an essential component of all living things that we know of. The DNA that we're built of, which is in every one of our cells, which is what reproduces us, is vital to life. It's so vital that we have 2 main strands in chemistry. We have those things which involve carbon, known as organic chemistry, and those things that don't involve carbon. They're all the other things. And that's the inorganic chemistry. That's how important it is to us that we have a whole strand of chemistry. And organic means derived from living matter in effect. So that's what, when we're growing organic things, it's relying on pure carbon compounds, not other artificial compounds. Now, here's an interesting one. I put this slide in for a material motive, but to start with, where's the carbon in this picture? It's basically everywhere, isn't it? All of the greenery behind will have carbon. There's a lot of carbon in that. And the wood, the tables, and even the varnish on the table will have carbon. The plastics, it's plastic or the natural resins that we use. And in the glass, well, the glass itself, there's no carbon in glass, but the bubbles in the water are wild. This is to introduce the issue that carbon moves around. What's in the bubbles is carbon dioxide, which has been put in the water. We put it there to make it fizzy. When it goes into water, carbon dioxide combines with water and makes carbonic acid. And that's what gives it a nice tangy taste. It's actually an acid in the water. But there's a natural balance of the carbon dioxide in the water and the carbon dioxide in the air. And so when you let the pressure off and make it warmer, the carbon dioxide comes out of the water. It doesn't stay in there, it wants to get out because there's this balance between the two. So depending on the pressure and the temperature of the carbon dioxide will go across that barrier. So you get bubbles formed and it goes flat. It still has a bit left in there, but it's so weak it doesn't have that same tang. Now, so we've got that issue happening in the sea everywhere around the world. The sea absorbs carbon dioxide. When there's more in the air, more goes in. There's less in the air, it comes back out again. So there's that balance. And it depends on the temperature right there. So carbon is the ultimate mixer. It moves around all over the place. And you guys would know better than any that there's a carbon cycle in nature. We've got animals. We need the food by eating plants or other animals. They get their carbon from that source. But where do the plants get it from? They don't get it out of the ground, which a lot of people think. They get the carbon out of the air. So all of the carbon that's in our food has actually come from the air. And, or just about all of it. It's certainly all of the plants' carbon comes from the air, and then animals eat plants, and so on and so forth. And we might eat animals that have carbon, but it originates from the air. So things go around in cycles. And of course, we breathe out carbon dioxide that goes into the air. That's what the carbon is that the plants use to grow. So we've got that cycle happening. But there's also other cycles in there, like decomposition of material, of composting and so forth. Carbon is given off then, but some of it's left in the ground. And in the ground, if it doesn't completely decay and gets buried and left under the ground long enough, it will convert into coal, where everything around it sort of disappears and leaves the carbon behind. Well, not quite, but you get the idea. And of course, you've got fossil fuels that are generated by that, which are a source of energy, and they burn, and that brings the carbon back into the air. So that's the basic cycle, but it's a lot more complicated. There's carbon in every area of our environment. It's in the water, it's in fish, animals, plants, in every nook and cranny. It's the basis of life. So everything living is living things everywhere, right up to bacteria kilometers above the earth to bacteria that are kilometers below the earth in the rock. We've got life in all of that planet, and there's carbon involved in all of that. And of course, I won't go through the details here, but you see the figures. That's why I wanted to go. Hopefully, you can still read there are vast quantities of carbon locked up in different places. And there was, well, there still is, I suppose, a lot of carbon locked up in fossil fuels, as they're so called. You can see where we're going here. Okay, so there are effects that carbon has when it's increased and decreased in different places. If you add carbon to the sea, carbon dioxide, it increases the acidity. It makes carbonic acid, and there's a certain level of acidity that the sea has. As it warms, the carbon dioxide actually wants to get more into the air, so that's a positive. But also, as the carbon dioxide in the air increases, more of it goes into the water. And in fact, of all the carbon dioxide that goes into the air, the excess that we keep putting in, about half of that goes into the water. And so the sea is actually getting a little bit more acid at the moment. Land, the fertility of the land is impacted by the amount of carbon in it. And also carbon can help water holding the characteristics of soils. And of course, in the air, that's where it's been so controversial. Having more carbon dioxide or carbon in other forms, methane is another example, in the air changes the nature of our air. It makes it more of a blanket. So the solar radiation comes down mostly as light, but it leaves the Earth mostly as infrared at a different in a different wavelength. And the carbon dioxide in the air doesn't let the infrared out as readily as it lets the visible light in. And so we've got that imbalance. And the more carbon dioxide you've got in the air, the less it lets Earth release the energy that's come down from the sun. That's the basis for the greenhouse effect. So events that change the balance can happen. This is a catastrophic event that happened 65 million years. What have I got written there? 66 million years. I can 66 million years ago, you would have heard of the catastrophe that took away the dinosaurs. A massive asteroid hit Earth and created so much debris and dust in our atmosphere that it changed the world overnight. 99% of all living things basically died as a result of that. 75% of all species were wiped out. There wasn't enough of the species left to be able to recover. It was a catastrophic effect on the Earth. And of course, the carbon dioxide level changed enormously because you've got this sudden hole in the Earth, lets out a lot of carbon dioxide gas, but also a lot of dust, and it changed the atmosphere, the climate, and the carbon dioxide in the air considerably. These things happen, but a modern question of balance is this. We have, basically, we've got the carbon that's in plants and animals, and we have that in atmosphere and the sea. They're the biggest sinks of carbon in the world, and they generally move between that in the soil. What has happened over millions of years, though, we have had lots of carbon built up in the Carboniferous period you would have heard of, which millions of years ago, and it lasted for millions of years. We had fossil carbon building up, time when trees didn't rot, and so when they fell over, they died. Lots built up in the forest, and there's a whole layer of those trees became sediment, and that got covered with other sediments and became the layers of coal we have. Similarly, in the sea, we have the we had seas which were stagnant, that is, they didn't have much oxygen in them, and the algae which grew on the surface in the very warm conditions would die and sink to the bottom and be left as a source of carbon, which was left as like a sludge at the bottom, and then that got covered with other sediments, and that became layers that came to be oil. So that's where our coal and oil came from, basically. And gas is a product of lighter elements from both the oil and the coal coming out of the soil. A lot of it would have been released over the years, but a lot stays into wherever you've got non-porous overburden. So over millions of years, lots of fossil carbon has built up. And in just 200 years, we've released a lot of that back into the air. That's our overall problem, a lack of balance in the system. It is easy to discount that carbon dioxide is a problem. The atmosphere is a big space, and CO2 in the air is good for plants. It's invisible, it's non-toxic, well, not in small quantities, it's only 0.04% of the air, so you wouldn't think it was a big thing. 400 parts per million sounds bigger. 0.04% doesn't sound a lot. So what's the big deal? How much carbon goes into the air from a person? Well, a person exhales about 360 kilograms a year. It doesn't seem an awful lot, but it's a fair bit when you think about it. That's a third of a ton of carbon dioxide we produce each year. But if you look at a petrol car, it's 4.25 tons of carbon dioxide a year on average. That's based on Australian car average consumption. Humankind exhales an enormous amount, and we've got more humans on this planet than we've got more biomass on this planet in humans than their domesticated animals now. And we've got 4 times as much as what the wild animals were 100,000 years ago before we started getting involved. So we've increased our use of carbon and our expiration of carbon. We have 2.7 billion tons of it going in, which is just from humans, not from those other things. But all of the stuff that comes out of our lungs, all the stuff that comes out of our domesticated animals' lungs, has come from plants or other animals that have taken that carbon from the air. So that's part of the natural cycle. So that's fine. It doesn't matter how much food we eat and carbon dioxide we produce, as long as it's all sourced renewably. That's where the renewable, because it's coming from the air. But the problem is that our machinery, which is making a lot more, 10 times more than what we use as animals, it's getting nearly all of its carbon out of the ground, which had been locked away from a time when there was an awful lot more carbon in the sky. It's been locked away, and it's taken away. It's taken away the balance that we had. But I have trouble picturing things. This is an example of how much Australia digs up in coal. We produce, so-called produce, we dig it out of the ground, around 400 to 450 million tonnes of coal. Like, how much is that adding to the problem? Is Australia part of the problem? I look at the figure 400 million tonnes. I think, well, how much is that? So, is it this much? Is it a pile of coal that big? Well, that's a big pile of coal you would get. That's the Giza Pyramid. It's 147 meters high. Let's compare, I did the sums on this. Let's compare it. with, say, Australia's tallest building. Let's see how much coal we produce. So that's up in on the Gold Coast there. It's 322 metres high. Now think of twice that height. Couldn't fit it in the picture, so it's got perspective here to make it a bit smaller in the distance. And think of 1.2 kilometres across the base. That's how much coal we dig up every year. And I've double checked, I've triple checked these figures. That's accurate. It's just incredible. And like, yeah, we've got a lot of atmosphere, but it's not that thick. And that's 1/20th of the world's coal. Australia produces nearly 5%, 4.5%. So we've got 20 times that every year going into the atmosphere. It's no wonder things are changing. And it's not as if we are reducing our coal use domestically, but we're not reducing our exports of coal. This is how much they've increased since we learned about climate change. Now, yes, we probably reduced our domestic use, or gone up and down again. You'd think, oh, we're doing all this wonderful stuff with solar panels and renewable energy. Surely we must be reducing our coal use, but now we're actually increasing our electricity use to balance it. So overall, we're not really making too much headway, and it's a real concern. Now, I've had trouble finding these graphs on the internet because they don't want to publicise how much coal we're using. I found this other graph, which I've superimposed there, which is just the last few years. You can see the little graph there in the corner. And if I grow that, you can see like it looks like we're coming down, but it's not very much compared to the how much we've gone up. Anyway, the real test is how much carbon dioxide is there in the air and how much is it increasing still. This is a graph from Tasmania's Cape Grim. CSIRO have a weather station there, and they measure the CO2 and methane and other gases in the Southern Ocean's air that blows across around the Southern Ocean, the cleanest air in the world. And they've been measuring it since 1975 or thereabouts. And the CO2 level has been going up and up. And if you look at those two periods, when we learned about climate change and the last 5 years and compare them side by side, it doesn't look so bad on the graph, but you can see we're actually almost increasing the CO2 in the air now twice the rate we were 30 years ago. That's just incredible, is it not? And yet, you know, all of the work of the United Nations and the IPCC, and that's what we've got. Now, imagine how much worse it would be if we hadn't been doing the stuff that we have been doing. But it's not a good sign, is it? That's twice as far from net zero as what we're. Net zero is this. That's what we need, net zero. There's a natural cycle in Earth's atmosphere. It does, the carbon dioxide does go up and down each year. But it's got to a stage where it's hardly showing going down each year, as it just keeps going up. This really worries me. Temperatures will not stop rising, whatever we continue to pump out. So, like it's not necessarily us personally, what the world is doing. So the CO2 concentration does go up and down. It is a natural thing. CO2 has gone up between 180 and 280 parts per million over the last 300,000, what's that, 400,000 years on this graph. Humans, Homo sapiens have been around about 300,000 years. So we came in about a quarter of the way across this graph. And in that time, CO2 has gone up and down all by itself, without our help. And, well, so you'd expect things might have changed, and they have. Well, the earliest Homo sapiens have been around. I was just listening to something earlier today. Earliest humans, that is, other forms of humans, were around about 1.3 million years ago. So humans of some form or other have been around a lot more. Us Homo sapiens, just 300,000 years. So the temperature has gone up and down with that. And so that's where the ice ages come in. The ice ages have lasted for quite a lot of that time. And in fact, the higher temperatures, like the temperatures we have today, are a rarity rather than a common. They're not the most common temperature for Earth in that period. You can see the interglacial periods, which are the top of those peaks, don't last a particularly long time, like thousands of years, but we've had just 10,000 years since the last interglacial, where it's been a fairly static temperature and static carbon dioxide alongside that. But you can see there's a really strong correlation between the temperature of the Earth and the CO2 level. And there's no, it's obvious that it has a marked effect. And sea level changes. This goes back to my original topic. Sea level changes enormously. Now, it's funny, I remember when I was at primary school learning that Aboriginals probably came to Australia across land bridges. And they used to be able to get to Tasmania just walking across the land in between because the sea level was that much lower. So we've known this stuff for a long time. But like, we set sea level as a standard. We draw out our maps. I'm just helping my daughter do the plans for a home extension, and I'm having to put contour lines. And what are those contour lines measured in? Meters above sea level. We expect it to be stationary. We don't expect the sea level to change. And here it is. It's come up 100 meters. 100 meters since the last ice age. It's 100 meters lower. It's just this last 10,000 years that it's actually been stable. That's that tiny blip on the end of the graph just here. 10,000 years. We're talking 50,000 years. So if you look at that graph and think, well, what have we done? Have we added much to that CO2 concentration? Have a look on the right there. Can you see where the green line has gone? Can you see that down the back there? It's off the graph. Now, it's moved that much before, but it's not been in that range of the graph. It's off the graph. And temperature has increased. Oh, no, temperature has already increased. Okay, you can see it's increased just a little bit. The red line at the end. Sea level hasn't changed much. But I figure it could take a while for sea level to catch up because we've got this nice ice stuff which doesn't melt so quickly. It's got a lot of energy or lack of energy stored up in it. So it's using up a lot of the energy that's going through the system and keeping things steady. So at some stage it's going to go up there to holes. But this is a graph that was drawn up at least 15 years ago by James Hansen and others. If I put the figures up to date on this, keep looking at that green line, in the last 15 years, that's how much more has been added to the green line. There's only this much. It's not an awful lot against the graph, but in looking at the earlier parts of the green graph there, you'll see that CO2 doesn't generally grow that quickly in 15 years. The dots on this graph are 1,000 years apart. Yeah, the pixels. So 1 pixel wide is 1,000 years. These lines are not going as vertical as they are. 15 years and we've increased it enough to, it's 100 times at least faster than we have it happen naturally. And the temperature has continued to rise in that 15 years. Is quite visible, just that red line there for that. So, and looking at the time, I'm probably close to my end here. I could talk all night. As you probably figured, I won't. I've got other slides, but this is where I'd leave it. But with this thought in mind, the Earth is an incredible place. It's got all sorts of different uh, climate in climates in different places. The climate does change, and it's changing now. But it's changed in the past. See the area in Africa there, the very yellow area, the Sahara Desert. Now, that used to be a center of human civilization. Egypt is in amongst that, or it's just off the side. It doesn't look much more moisture there, does it? Just 4,000 years ago, I don't have the slide of this set, but 4,000 years ago, it was actually more of an oasis. There were big lakes in the middle of Africa, and there was a lot of human activity there. As climate change happened about 3,000 years ago, which was about when the Egyptians were at their peak, 3,000 to 2,000 years ago. But they've been around for several thousand years. So there was a lot of human things happening there, but I don't think that caused that particular climate change. I think that was caused by a change in the Atlantic Ocean currents, because Europe at that time then melted, and we ended up with a much warmer climate in Europe, England, that top end. And that's how it's become so grim, because the Gulf Stream and the currents in the Atlantic took a lot of the warmth and moisture north. These things change with time, so climates are not static, and they won't ever be. But we don't really know what the climate is going to do with what we're currently experiencing in the changes that are going on. So hold your hat on, because things are changing. Where will we end up? Yeah. But carbon is so important. Any questions? I haven't bored you to tears with all of
that. That's fantastic, Tom. We'll turn the lights on so you can wake up everybody. So we'll consider a couple of questions for a minute, because Tom's given us, we've always thought lots about carbon, but you now start to make us think a little more seriously about it. So questions from the audience? Or you've stunned them all.
Surely somebody's going to come back at me on something there, I've said. Come on.
Michael.
It is in relation to carbon, and there is a correlation between carbon and coal seam gas issues. The creation of all this carbon, coal seam gas, and that going to affect the balance of carbon in the future.
Yeah. I think what we're saying is coal seam gas a problem if we use coal seam gas? Is that basically? Well, there are a couple of problems in that coal seam gas is a fossil fuel. If we didn't use it, it would stay in the ground. And if we do use it, it will get burned and it'll end up in the sky. So that's the basic problem with all fossil fuels. So it doesn't matter whether it's coal, oil, or gas. If we dig it out, unless we make plastics from it, which you can do, and most of the plastics come from oil, in which case we're locking up the carbon in another form. If we dig it out in order to burn it, it ends up in the sky. That's the problem. But there's a second one for coal seam gas. It's this fracking thing. And fracking implies that's how you get it out of the ground. By basically you drill down in amongst the coal that's down there, and you pump. There are different processes, but basically you pump in liquids into the coal seam, so it expands the rocks down there and lets the gas free from the coal. So it's a way of getting the gas out of the coal, and then they suck the gas out, replacing it with liquids they've pumped in. The problem with that is it's also releasing things. It's breaking up what might have been non-porous rocks and making it porous. And so you end up with issues with the water that's down at that level, or water that's held in the Great Artesian Basin, for instance, being contaminated by the coal and gas that you're releasing, and you can affect the surface water. It can go down. So it's just that you're damaging perhaps the soil at the very surface, basically, in order to get the stuff out from underneath, and you're doing damage to things down there. You're releasing stuff out of the coal, but perhaps a best left alone. Yeah. So that's what coal seam gas is.
Would you say that we're on the cusp of another ice age, looking at those graphs and those graphs? And if so, would global warming help to prevent an ice age in the next 1,000 years?
You're right. Yeah, we were due, probably. I mean, we've been on this interglacial period of warmth for quite a while now, and you would expect in the natural cycle of things, if it stayed the same as it was, we would go back into an ice age. It's true, yeah, but we're not. We're actually heading in the opposite direction. If it might be a good thing if we could hold it at this temperature. That if we could, that's geoengineering in a way. It's basically, yeah, taking control of this natural mechanism. But we've overdone it. So if you want to hold the argument, yes, okay, to burn fossil fuel because we need to keep it warmer, that's fine, but we've overdone it. And look, here's a real blast for you. The dinosaurs lived on Earth for 160 million years, roughly. 160 million years. We've been around 1/3 of the years. The whole period the dinosaurs were here, Earth had no ice in the poles, virtually the whole period. The temperature is something between 8 and 20 degrees centigrade hotter than today. For the whole of that 160 million years, Earth is quite happy with a much hotter temperature. It's only this last little bit, I haven't shown you that graph, I've got it in other talks, but it's only this last few million years that we've had these low temperatures, these ice ages and so forth. Before that, it was a lot hotter. So I'd hate to think that we're pushing it back there. It's a long way to go, I know, but like, consider Earth more commonly over its whole lifetime has been a much hotter place than today. A much hotter place.
Sonia.
Yeah, thank you, Tom, for the chemistry refresher lesson and for really cool.
Thank you.
And that last graph that you put up, the 3 lines going up and beyond, very dirty. What do we have to do to bring that back down? And is there a time when it becomes like nothing?
Yes, it's a very good question. As you probably know, we're aiming for net zero, and net zero is not bringing that line down again. It's just stopping it going any higher. So if we can achieve net zero worldwide, we will stop putting carbon into the sky or have a balance there, net zero. That means that we would no longer be pushing it up. But my concern is that it may still continue. Once we've stopped, it could still get hotter, and certainly sea levels will continue going up, whatever we've got it warmer than what we should have it, what we'd like to think we should have it. So it doesn't look very positive if you look at it that way. Now, we could start to bring the temperature of the Earth down in other ways. It doesn't look as though we've been really successful at stopping carbon going into the sky. There are other ways of cooling it. There's something we've been doing which we didn't really mean to be doing, and that's putting particulate matter into the upper atmosphere. Sulfur and other contaminants, particles up there, act as like a sunscreen. They bounce the radiation back out again when the sun's shining on us. Just recently, over the last few years, the authorities worldwide have got chips to stop burning so much sulfur in the fuel they burn, so they don't put so much particulate matter up there. And there's been a marked, in fact, measurable effect on the climate. It's actually making us warmer because they're making the atmosphere clearer on that one. But the same process could be used as a geoengineering technique. We could pump masses of salt water, spray it into the upper atmosphere, which could be done from the lower atmosphere, drop it up there, and basically create salt crystals up above, up high in the atmosphere, and bounce the sunlight out that way. So we could actually keep some of the heat out and stop the Earth warming that way. So that's geoengineering. That's one of the techniques you could use. But the difficulty with that is the politics. If country A started doing it here and it affected the rainfall in country B here, who's going to pay for that? Or, you know, what's going to happen? So you've got to have a worldwide and we haven't even started testing that technology.
Susan.
The amount of fuel that's underground, how much longer, how many years is there
How much?
how many years can you keep pumping it out of the ground?
How much more is left in the ground is what you're asking.
And how many years at the rate exponentially?
Yeah, the different forms of it. Oil, they say we passed peak oil, but I'm not sure. They keep finding more. It's probably as much left in the ground as what we pumped out. I don't know for sure on that. But coal there is. Well, I remember.
That's not very long.
You'll love this story. I remember a talk I attended when I was 20 or so. This new environmentalist, Bob Brown, came along to talk to us, and he was putting down nuclear energy while I was saying, well, nuclear is not too bad because you really can contain the pollution from nuclear, whereas all the other pollution in the world comes from these other fuels we use. I wasn't an environmentalist back then either, but and he said, no, it's nonsense, Tom, nonsense, because there's enough coal under the Sydney Basin to burn for 200 years, he says. This is Bob Brown. But he's changed his tune on. But like there's enough coal in Australia. We've got an enormous quantity of coal. It's lower and lower grade coal, or thinner and thinner seams, but there's a lot of it there. It would keep us a couple of 100 years, probably. But we're actually growing our use of it worldwide, so whether it would last that long, really. But will we be able to survive it? Is the question. Yes. Well, oil is less. So.
Another question?
That was a rather long answer.
Yep.
Sorry.
Go ahead.
That's graph showing the cycling of temperature and carbon. What's sort of the mechanism that cause that to happen?
The mechanism that causes the temperature and the sea level to come down along with carbon dioxide is basically that carbon dioxide acts as a blanket in the atmosphere. So as you increase carbon dioxide, there are there's a complex equation, exactly the correspondence there, but it's like a reverse exponential. So if you double the amount of carbon in the air, it adds extra degrees to the temperature. You can double it, so it becomes less effective the more carbon you add. But as an example, back in the dinosaur days, the carbon dioxide in the air was something around, I'll tell you what figures was, 5,000 parts per million, as opposed to 280 parts per million was what we came from. So 5,000 parts per million was a lot more carbon dioxide in the air when the temperature was 8 to 20 degrees hotter, and so on. So there's a direct relationship. It's not the only thing. Carbon dioxide is not the only thing that changes the temperature of the Earth. Other things have an effect. The Earth's orbit does change. It gets closer to the sun, or the inclination to the sun changes. and these things can happen. But carbon dioxide has a direct relationship in the sun.
Brian.
Just a comment on coal seam gas. Methane, of course, is an extremely good greenhouse gas. Not by itself. Forget about burning it. By itself, it's a nasty greenhouse gas.
Yes.
One of the ways we can reduce climate change or do something to climate change is stop coal mining because that releases coal seam gas.
Yes.
Also, natural gas, as it's called, all the natural gas installations, methane, like nobody's business, that's contributing to greenhouse. Well, the only good thing about methane is it doesn't rise to the atmosphere, carbon dioxide. So we should be bending our sinews to try and stop all coal mining and all natural gas handling at all.
Exactly right, yes.
It's much easier to try and get rid of carbon dioxide.
Yeah, I agree. We really should stop putting all of these things together. The reason methane isn't seen by some as so bad is because it naturally disintegrates in the air by itself, but it takes a long time. There's something it's got the heating potential at 30-something times CO2, so yeah, it's much worse gas. The other thing, of course, is that people are seeing gas as a solution. The likes of our politicians who see a gas-led recovery want to replace coal and oil with gas on the basis that gas is a much better solution. Well, gas has got one carbon atom, methane, one carbon atom has got 4 hydrogen atoms. When you burn that hydrocarbon, it produces less carbon dioxide and more water. Hydrogen atoms go off into that water, which is, of course, not a problem. So when you burn it to get the energy out of it, you get less carbon. So, yeah, it's about 50% when you're burning methane as opposed to other fossil fuel. So it reduces the amount of carbon produced in order to get the same amount of energy. But the problem is, as you said, when you pull this out of the ground, a lot of it leaks. And also you need a lot of energy in order to compress that methane gas, in order to put it in containers and ship it overseas. And you're creating more CO2 from burning gas to create the energy to do that. And so by the time you've finished off looking at gas, it's really not much better than burning coal or oil. Stop burning oil.
Okay. Kim? Yep. A question. Yep.
Just looking at the map up there, we've got much more ocean than we have got land.
Yes.
Correct?
Yes.
So what role does the ocean play in comparison with the land in moderating the range of variations in temperature of the Earth? And is the Earth's temperature measured by a combination of ocean temperatures and land temperatures?
It's a really good question. This is one that I looked into too. The temperature rise has been measured at around 1.5 degrees on average. Is the surface temperature of Earth. That's the land surface and the sea surface. Now, sea is deep. It's an average depth of 3 kilometers. So we've got 3 kilometers of sea there. And here's a little statistic for you. If you heat all 3 kilometers deep of sea by 1 degree, you get 1.8 meters of sea level rise. So when we have increased the heat of the whole sea by 1 degree, you have 1.8 meters of sea level rise. That would be catastrophic. We've increased the surface by 1.5 degrees. In fact, it's not quite so bad on the sea. The land tends to be more variable. So we, on average, 1.5 degrees Earth, but the sea tends not to be heating quite as much as the land, which is heating more. So the land is 2 to 2.5 degrees, or the sea is probably only about 1 degree more. But that's just the sea surface. Now the sea cools down to just I think it's 4 degrees centigrade quite quickly as you go down, and it stays about 4 degrees centigrade almost at the bottom. And it hasn't changed down there yet. Only the surface has warmed up. When it does change, we'll have 1.8 meters per degree of sea level rise just through thermal expansion. So while ever we hold the temperature of the surface of the sea, I haven't tested this or seen research on it, but if we hold the temperature of the surface a degree more, I would expect, since there's heat coming from the centre of the Earth outwards, eventually the whole sea will warm up by 1 degree. And so we're going to get that sea level rise. Earth is the same. The rock that makes up our land is going to be the same thing. It will take a long time for that heat to sink in and for the whole body. Now, I figure that if we hold the temperature of the surface for any length of time, and it looks like it will be, don't see the CO2 going anywhere, then it will just continue heating the surface, because the warmer it is underneath, the warmer it will get on the surface.
Thanks, Tom. Janine?
We've heard about a lot of artificial, I suppose, sequestration sort of processes. Has there been any sort of progress on that sort of front, rather than using forests, etc., and planting forests? Has there been any progress there?
I haven't seen any great progress on the carbon sequestration. They've seen this as a magic bullet for those places that produce a lot of fossil fuel. Power stations where you're burning a lot of coal and you're producing a lot of carbon dioxide. So it's concentrated carbon dioxide in your chimney. Hey, wouldn't it be good if we could just take that out and put it back in the ground? Well, there's a couple of things that make this rather difficult. Firstly, that when you join carbon and oxygen, there's CO2, so there's 2 oxygens, and oxygen is a heavier atom, so it's actually more than 3 times the weight and volume of the carbon that you burned that you're trying to put into the ground, so it's bigger. And it's also a gas, so making it stick is difficult. And carbon dioxide is poisonous in small quantities, but in large quantities it's catastrophic. And it is heavier than air, so if you have it underground and a little seeps out, there's been examples of whole villages, not for this sequestration, but for other reasons. Carbon dioxide comes in and everybody suffocates, dies. So it's not something we want to really play with too much. But it's a magic bullet for the fossil fuel industry if they could do that. But so far it's proven to be too expensive. And look, it's actually cheaper to leave the coal in the ground in the first place and use renewable energy.
Last question.
You're on it, Graham. Thank you very much. My question is about the fact that you mentioned earlier that increasing CO2 level in the sea, the acidity, and I think that's something that a lot of people don't realise forget, because that has an effect on the
marine life.
Yes.
Sure. I haven't looked at this in great depth, but it's obvious that if you increase the acidity, then obviously it will change things for sea life. And I do understand that that shellfish in particular have more and more difficulty creating their shells as the acidity rises. And there are areas of the world where they're getting to the stage where those sea creatures, the shellfish, are no longer able to produce shells of the quality that they used to, and it's affecting them. So yes, as the sea level, the sea acidity increases, it's going to be more difficult. The sea temperature increase is also going to impact us in other ways. It's not just that certain creatures will die, but they'll move that way. And I don't know whether anybody here has tried to swim in Queensland waters of the sea, but I wouldn't want to have problems that Queensland has in New South Wales. having to wear a suit to keep the stingers off. Yeah. And we've already got sort of an increase in box and so forth happening. But warming seas is going to have various effects. One thing, and like the algae growing in South Australian waters is another, where we've basically got a lack of oxygen and the sea life is dying.
That does come up. Tom, a very, very engaging presentation. That's going to wrap up with a vote of thanks.
Thank you. I don't know if I need the microphone or not, but I'll use it. Hello, everybody. Good to see you again. Haven't been for a while. On behalf of everybody, Tom, I think it's fair to speak for everybody saying that you gave a lot of information that was very interesting, and a lot of it was new to me. I didn't know some of the concepts of it, but it's always good to be told and shared new things. And it's obvious to all of us, I'd say, that a lot of work is on this, and we're also very passionate about it. So we'd like to present you with a copy of this year's calendar as a way of saying thank you for your efforts, and also a round of applause if we could.
Everybody, have to get at 9 o'clock, and I much appreciate again to Tom for coming up from Wollongong. I'm sure if you've got one or two other questions, you can grab it before he leaves. But again, thank you for your attendance. We've got 40 folks here in the hall tonight, another 5 on Zoom. So we actually have, Tom, you've created a mini record here. It's not quite the record, but very close. Thanks again for coming. It's been wonderful to meet up with you. We've learned a lot tonight. Thank you, everybody. Have a good evening, and we'll see you on one of the walks or one of the other activities, or back here next month. Thank you so much. Good evening.
Okay, good.